Welcome. My name is Jorge Torres. I'm the CEO at MindZB, and I'm here to talk to you about what we do at MindZB, which is to bring machine learning to the database. And my coworker Patricia is actually going to walk you through some of the really cool problems that MindZB can solve for you. Let's start by the question that we asked ourselves when we started building MindZB, and that is machine learning, where does it belong best? To give you context, imagine of the application stack. You have the data layer, which is where your databases are, your data lakes, your data warehouses. And you have the application layer, which is where you actually build your actual application. So that's where you code in Python or C++ or Java. And then usually you have the presentation layer, where you actually code how you present the user interface to your user. So this is where you have like the HTML, the JavaScript, the CSS. Most of today's machine learning tools and machine learning solutions are built within the application layer. And this makes sense for a lot of problems where you may necessarily want to, or your data doesn't come from a database. Say you want to do classification of images or computer vision and that type of task, self-driving cars. Now, there are problems though, where if your data is already in the database, and that's the data that you want to use to train a machine learning model, it may make sense for you to treat machine learning as another building block within the data layer. Let me actually walk you through how that actually looks like. Imagine that you have a table somewhere in your database or document or something that you're actually storing and querying. You can think of each of the rows as a dot in somewhere in space. And a machine learning model actually is, a hyperplane that tries to fit all that data that you have. You can think of a model as something that you can query the same way that you could query a table. And instead of getting discrete points, you're going to query over a surface. Let me actually tell you more about how this works and the intuitions that got us into building machine learning at database. So the first thing that we start to realize is that people tend to reinvent the wheel over and over in two basic paths. The first one is the ETLing involved when you have to do machine learning at the application layer. And this is because even though your data may live in a database, when you think of the application of machine learning, you also start thinking of doing transformations at the same place where you're actually having your application. Now, databases have been building transformation capabilities and ETLing capabilities for such a long time that perhaps it doesn't make sense to reinvent this. However, when we build it as an application or build machine learning as an application, we tend to do a lot of that transformation and a lot of those things that databases may provide for you already within the actual application. And maybe that's not the best idea. Now, the second thing is once you want to move your model into production, you end up reinventing this wheel over and over. Most people wrap their machine learning models around a web interface or a web service. And now you have to maintain not only the model, but also the infrastructure to serve this model. And lastly, if you want to consume this model and say use these predictions for something useful, now you're going to have to pipe data again into the machine learning model, do the transformations there, and then query it for some results or ask for it for some predictive results, get this information back to where you need it. And that in itself involves some other forms of ETLing. Say, for instance, you want to use it in a BI tool. Now you're going to have to extract all the predictions and store them somewhere so you can actually use them for your BI capabilities. On the other hand, if you think of machine learning as a building block within the data layer, the stack looks very similar, if not the same as what most developers are used to today. You have the application, and then you query the data layer for the data you want. And now you may have the capability to query for data that exists in the database or for predictions that are being generated from information that is in the database. Now, to make this possible, we created this very simple abstraction called an AI table. An AI table allows you to see predictive machine learning models as if they were database tables. Let me give you some more intuitions behind this. Imagine that you have in your database a very simple table. It has two columns, income and debt. Think that you can visualize these two columns like this, where you have the Y and X axis, and you have each of the rows as one data dot in this plane. Now, if you query this table and what you're actually asking for has an exact match, there is a row that matches your query, you're actually going to get a response. So say, for instance, select where income equals 8,000, there is an actual row that you have in your data that has this information. However, if you query for a data point that is close to the data you have, but not an exact match, you're going to get a null. Now, you can think of a machine learning model as a surface that covers this point, and it would be really cool if you could query that line as opposed to querying for the specific data dots that make up this line. And that's exactly what we do. We allow you to publish that model as a table and query it just the same as if you were querying a table, but in return, you're getting predictions or forecasts. Now, but is to walk you through some of the very interesting problems that arise once you start treating machine learning models as tables. Stay tuned.
Thank you, Jorge. I will now take you through the advances we've made at MindsDB for multivariate time series forecasting, which is a very common use case, at least on the feedback we've received so far from the community. So let's start with a simple example to showcase why this is a hard problem. We're going to consider a dataset that's retrieved directly from Kaggle. It has to do with electrical power consumption in India. As you can see here, a few rows of the dataset are shown. And you can see that for each daily measurement, there is an associated electrical usage for each Indian state. And there's, of course, some additional information like on which region the state is, as well as some georeferential information. But the important thing is that we have for each different state some daily measurements that define the electrical power consumption. And so this, if plotted, would look something like this. We have some of the dates in the x-axis, and then the power consumption itself. As you can see, depending on which pair of states you choose, the temporal dynamics of each time series will be fairly different. So this, we think, showcases some of the challenges that come with forecasting time series. So your team of data scientists or machine learning engineers or whoever runs the predictive insights at your company will have to be aware when creating the data pipeline, the ETL process, that there's going to be more than one single time series. And what's more, depending on how you group your data, it might be possible that you will have orders of magnitude more series than what's shown in this example. So you could think of not only grouping by the state, but also the city, for example. And then we could have 10 times more series here. And it would be perfectly valid still to think about forecasting for those, right? So having such a high cardinality in your data whenever it has a temporal component makes things a little bit more complicated, because training machine learning models is a very compute intensive task. and you want to be efficient about the use of resources. In fact, if you were to train a single model for each series and you had, say, for instance, 10,000 different groups, like that situation would probably not scale. And we have seen these challenges firsthand while developing our solution for this. And so now MindsDB is at a point where it automates most of the pain associated with going through, setting up a forecasting pipeline for temporal data. So we'll be taking a look now at how it is that we achieve this. In no small part, the success we've had with our current approach is due to our flexible encoder mixer philosophy that you see in this figure. Now, this is how MindsDB really operates, not only for time series tasks, but for any other type of task, like numerical, categorical, or text predictions, right? So the general pipeline here is that we have a certain data type for each column in the dataset. And after a pre-processing step, we encode, we learn to encode the data of each column so that we obtain a more succinct representation of what's going on in those columns. The information then passes through a mixer, which in essence is the final machine learning model that is tasked with predicting, in this case, the future values of each time series. And the cool thing here is that you're not really limited to having just one column per each data type. You could have multiple time series columns. And this is where the concept of multivariate time series comes in. So basically, we're aiming at forecasting the future values of your series, but not only based on the previous values of the series itself, rather you're also observing other series that might be present on your data set, but on top of that, you might have non-temporal features. So numerical records or categorical records that might give you a better idea of what to expect, or that's at least what you would hope the model will learn, right? So with this philosophy, we go through, pre-processing the data, then some sort of learn feature engineering step, where our encoders might be very simple or very complex, depending on the type of feature. For example, our text features are encoded with a state-of-the-art transformer neural networks. And then the mixer can also be, there's a couple of different mixer flavors that we'll take a look now. So before going to that, a very important thing that is specific to time series that we've learned to automate at MindsDB is the fact that you will usually want your machine learning model to predict using normalized input values. And what this means is that for this example in the right that you can see here, it has to do with the number of late arrivals of airplanes in the US airports. In this case, we've grouped those records by each airline carrier, and we have some, a dozen or so different time series. And if you notice, the one that has the least amount of transactions per time goes between 0 and 500 late arrivals per hour. However, the carrier that has probably the most traffic has late arrivals that go through anywhere from between 3,000 to 4,000 events per hour. So that's a very big difference in magnitude. And the interesting part is that MindsDB receives all of the temporal information of the series in a normalized way because we store the statistics of each one. And then we use those in a way that makes the mixer learns to predict, but in a scale agnostic way. So when you forecast, you don't really care or have a worry about how different the scales in your series are. The predictor is going to not only forecast both of them, but learn from all of them at once in a single machine learning model to get better forecasts. Just to delve a little bit deeper on the mixer side of things, this figure up here shows a summary of the previous one, But in this case, focused entirely on the time series tasks. So up here, we have the stream of non-temporal features that get encoded and then passed onto the mixer so that it is aware that they exist and have some values for each data point. But there's also the temporal features for which in each time series, remember we can use multivariate time series, so meaning several columns that are temporal in nature are used to forecast the next value of the target variable. And in this case, you have the stream that goes through the normalizer, then it gets like a temporal infusion of information using, in this case, a recurrent neural network. And finally, it gets passed to the mixer as well. So there's some sort of special treatment for anything that's temporal here. And we offer two types of mixers that complement each other very well. And at the end of the day, we select the one that performs the best on some portion of some held out portion of the data. So there's a neural network mixer that, that its design is basically, it turns into two streams of data. So the first stream of data has a learned autoregressive process. That means the mixer learns to look back to the previous values of your series, and it gives a rough initial prediction. And then a secondary stream uses more advanced computations to fine-tune this prediction. On the other hand, we have a gradient booster mixer, which behind the scenes uses the very performant and fast LightGBM mixer, which is open source. We're open source as well. And we actually leverage Optuna, which is, funnily enough, another open source library to do hyperparameter search. So if the user wants to, they can do a very thorough model selection phase for the mixer itself. Now, going back to the India power consumption example, we believe that the main avenue to use machine learning models, as Jorge previously mentioned, is at the data layer. It is what we think makes the most sense, and so the showcase in this case, like in this presentation, will be through SQL statements. So the way you would train a predictor in this for this data set would be to simply insert into the predictors table a predictor with a certain name, with a target variable to predict for. Then you pass an SQL query that will retrieve the training data for you. And in here you can do, you can define a temporal cutoff for your data so that the predictor only uses up to a certain date of the data set to train. And then there's the parameters to train the predictor, which in the time series case are actually very important because they define by which column you will order your rows by. They define what's the grouped subset of columns that you will choose. In this case, it's only the states columns. But this is important because it defines like how many series you actually have. And then there's the window parameter, which means like how many rows into the past the predictor is going to consider to make its forecast. You can also add here like the number of predictions into the future you want to see. So the forecasting horizon. And those are all very important parameters that you might want to use. So once your model's trained, you can query it on two different ways. You can condition your predictor on some values that you want to give your data point. So in this case, you would be predicting the usage, like the power consumption usage from the predictor whenever the date time stamp is this particular value. But for whenever you want to predict a bigger amount of data, so basically when the model's in production and you're getting true predictions out of it, what you want to do is actually join the predictor with the table that has the query data in it. And if you notice It's as simple as doing a left join in this case. And in all three code blocks with SQL statements, we've treated the machine learning model as just another table. And this is, to us, what makes the most sense, really. The way that this looks, so once you've trained and forecasted some of your query data, you can get visualizations like this one. So here we're looking at the Pondi state in India. The green line is the actual time series. The purple line will be what MindsDB thinks is going to happen the next day. So this is what we call the T+1 forecast. And an interesting bit here is for each point prediction, we have an associated confidence estimation that lets us define an upper and lower bound of, like, basically turning the point prediction into a region. And this lets us do a very cool thing, which is anomaly detection. So whenever the actual series data point falls outside of what the predictor thought, we tag the data point as anomalous. And so the user can take a closer look and see what's going on. So in this case, for example, there's a drop in here that's very noticeable, and it gets flagged as an anomaly. So if you're an administrator at the power plant, you might want to, be alert for the following day. But that's, as we previously mentioned, that's not all. You get, with the same predictor, you get forecasts for any other state as well. So you get a machine learning model that's able to train for and then query all of the groups in your grouped data, which is pretty powerful. Now, that was the previous visualization was for the next day, for the T+1 forecast. So what happens when you get, when you specify longer horizons, right? This is a video that shows a different data set. It has to do with the number of, I think, cars that pass through a certain highway segment. And in green, you've got the real actual series. In purple, for the past values, you've got the last prediction that MindsDB output. And for the future time steps, you have what MindsDB thinks will happen as far as 20 hours into the future. So this is a data set that has hourly measurements instead of daily measurements. And if I play this, you can see that the peaks in the data can be modeled in some cases as far as 20 hours from the current time. So what this short example shows is that you can get insights further into the future whenever you want to set a longer forecast horizon with our current approach. So that's also possible. Okay, well, I hope that has given you a decent idea of where MindsDB capabilities are at right now regarding time series. But of course, we're always looking to improve, and being an open source solution, we're also always glad to accept any help from contributors. So if you guys think this is interesting and you want to collaborate, we would be happy to assist you in and see how we can integrate your ideas. So some of the things we're currently working in are predicting from data streams. So think Redis or Kafka, which are quite powerful tools. The concept here would be to have a predictor that's constantly listening to a certain stream. And whenever data comes in, the prediction will get output in a different stream along with the confidence estimation, the lower and upper bounds, whether or not the data point is an anomaly, etc. And we think for real-time, high throughput scenarios, this is really, really valuable. There's also a current challenge that we're seeing that has to do with predicting for longer horizons, but in cases where you have lots of non-temporal information. And the issue there becomes, how do we actually predict what those non-temporal columns will look like in the future? And that's a very challenging subset of the task that we're trying to improve upon. Then regarding anomaly detection, we're trying to detect gradual anomalies because our current approach is very good at sudden anomalies, but there's lots of them where you have some sort of drift on one of the variables, and that's much harder to detect with the current approach. So it is something we're exploring. And then finally, there's another library called Modin, which enables using GPUs for data frames. And MindsDB internally uses pandas data frames from Python. So integrating Modin, or rather MindsDB with Modin, will enable us to be much faster whenever you train and or use a predictor. So now I would be very happy to take any questions that you might have. However, I believe we're going to move to a demo now, where I'll show you like how this actually looks when you're using it. So we can leave the questions for the end. You can find both Jorge and me in GitHub with those two handles. And yeah, here's a QR code for in case you want to check out MindsDB and start playing with our time series capabilities like today even. So thank you for your time. All right, so welcome to this demo section of the webinar, where we'll be taking a closer look at the India power consumption example, actually going through the motions of how you would use MindsDB with it. So I've got here a terminal, and the first thing you want to do is set up or start really MindsDB with both the HTTP and the MySQL API with a config.json that has some parameters that are not really the focus for this webinar, but they simply set up the connection. And this will, connect to the database where we store the predictors, connect to the other databases that we use to load data from, and it will fire up the GUI of MindsDB proper, which has a tab for datasets, a tab for the predictors themselves, and then for queries if you want to query them. So another thing we will be using is a BI tool, which is called Superset, and it's also open source, which is in part why we want to showcase the visualizations with it. And I have it on this port. It is now running, perfect. Okay, so with that in mind, we now turn to our MySQL shell. And the first thing that you would want to see here is the data, right? And so we have several data sets in this case, which are not really, they're not all relevant to the webinar, of course. So we will just go with the power consumption one. And actually we will go with the testing split, because we want to see like how the data looks regarding the date timestamps, right? So if you see like the, if we order by the date, you will see that it starts on the 1st of April of 2020. If we go to the training data set, which is called like this, you will see it starts in the 7th of January of 2019. So it's quite a while before. And in both cases, we have, as we previously saw, the states, their associated regions, their latitude and longitude, the date where the measurement was taken, and then the measurement itself, which is the power consumption that we want to forecast. Okay, so now we want to use MindsDB. And as previously discussed in the presentation, the way to do that is through a single SQL statement that looks like this. We are currently in the MindsDB database, which is created whenever you connect, in this case, MySQL to MindsDB. And we're just going to name this predictor India Power 2 because I already have one stored to avoid waiting for 10 minutes, which is what this predictor takes to train. And compared to the slides, the only difference is that the select query for the training data specifies the columns and the actual table, which is the training table that has 15 months worth of data. And yeah, so we specify that you need to order by dates, group by states, which defines the number of series that you forecast for, and the predictor will have the past 10 values of each series to use for forecasting the new value. And the query is processed okay. If you notice in MindsDB, we now have actually a new data source that's related to this predictor, India power number 2. And in the predictors phase, you can see we have we have this predictor, which is now being trained. And you can, of course, go to the MindsDB log and see how it actually reshapes the data into time series format. It before this, it analyzed the data, it cleaned it, split, transformed, and so on. So there's a lot of the machine learning pipeline here that's actually automated. And it was just with one single SQL statement. Now, as this takes 10 minutes, if you actually select from the predictors table, you will see that the predictor is currently being trained. So that's in line with what we would expect. But we actually want to query from the pre-trained version. And so to do that, we'll use the type of query that has to do with batch prediction. So basically, we will select the dates, the states, and the power from a query table, which is this one, the 2 months for testing. And from the predictor, which is P, we will get the actual forecast using a left join on both ends. And this will take a little while because it's forecasting for 2 months of data. But once that's done, what we can do is actually import this from Superset, which is the tool that the business intelligence tool that I talked to you about before. Here you can just see, like this is the log of MindsDB, what it predicts every single data point. Not really relevant, but if we go to the Superset tool and we go to the dashboard that I prepared for you in advance, we already have the results of those forecasts. And here are 6 different states. So we can easily see the difference between the forecasted quantity, which would be belonging to the sum of the power, versus the actual series, which belongs to the previous target. And you can go into detail on any of the states here. In this case, I'm showcasing 6, but getting a dashboard set up for a new one would be trivial. And yeah, you can easily get a notion of how good or bad the forecast was. So in this particular state, the Bihar state, this is in blue, we have the actual forecast, and in orange, we have what happened. So we can see that there are some spikes here that are not really anticipated by the predictor, and so it would probably flag it as an anomaly. But this is just a very quick, simple example of how you can easily integrate external business intelligence tool with MindsDB, thanks to our approach of exposing machine learning models at the data layer. So yeah, that's mostly it. This is a very short demo, and I hope it gives you a good notion of what's possible with our AI tables. Thank you so much for your attention, and we are now open to any questions you might have in the QA live session.